In this lecture on compact sets in R, we will be uh, giving the definition of an open cover of a subset of R and its subcover. We will also define what is a compact set and look at several examples. So let us begin by defining open cover of a subset of R. Suppose A is any given subset of R. And suppose that you are given a family of subsets of R, U alpha, where alpha belongs to lambda. So lambda is the index set, and for each alpha in lambda, you have an open subset of the real line U alpha, and you're looking at this collection. So this we want to say that this is an open cover of A if A is a subset of the union of all these U alphas. So if A is a subset of union alpha belonging to lambda U alpha, then we say that script U is an open cover of capital A. So capital A is the subset and script U is a family of open subsets. So since we are calling it an open cover, of course there are possibilities of other types of cover, but we are not interested in that. We are only interested in open covers. So by an open cover, necessarily you mean that all the subsets in the family which you are considering are open subsets of R, and you denote this family to make it clear that what we wish to say here is not necessarily a set of sets, which leads to logical pitfalls. We give it a notation by writing this fancy U or V or something like that, and instead of capital letters. Okay, so this is our definition. So the definition doesn't involve much to understand. All you need is that you have to take the union of all the subsets in that family. It will give you a new set, and this new set should be a superset of capital A. Then you will say that the family is an open cover of A. Okay, so let us start by looking at some examples. So the first example is a very simple one. Just look at the positive real axis. That is, look at the open interval 0 to infinity. Then this family, so this is my family script U here. This family consists now of only one open set. Okay, and this open set obviously contains the set of positive integers as a subset, because what are positive integers? They are just 1, 2, 3, 4, etc. These numbers, right? So they are all greater than 0. So they will all belong to the open interval 0 to infinity. So therefore, since n is a subset of open interval 0 to infinity, therefore this singleton is an open cover of the set of positive integers. So it is a very trivial example, right? Similarly, let us look at another example. So you have these numbers 1, 2, 3, etc. That is a set of positive integers. Now you look at the open intervals n minus half to n plus half, where n is a positive integer. So now what you're getting is, you're getting a family of open intervals, and here your index set, which was lambda in this case, in the general definition, the index set here is the set of positive integers. So there are countably many open intervals in this family. Here there was only one, so here lambda is a singleton, right? Lambda is just one. The set lambda consists of only equal to 1, right? And here the lambda is equal to the set of positive integers. So this is just a singleton, this family, and this is a countable family, countably infinite family of open intervals. And what does this look like? Very easy to see that if you look at 1, for example, then you will get 1 minus half, so that is half, to 1 plus half, so that is 3 by 2, right? So you get the open interval half to 3 by 2. When you put n is equal to 2, then you get the open interval 2 minus half. So you get 3 by 2 to 5 by 2. Similarly, for n equal to 3, you will get 3 minus half. So that is 5 by 2. Right? 3 minus half is 2.5. So that is 5 by 2. And 3 plus half. So that is 7 by 2 and so on. So you get these open intervals. They are all disjoint. Notice 3 by 2 does not belong to the open interval half to 3 by 2, and 3 by 2 also does not belong to the open interval 3 by 2 to 5 by 2. But if you look at the union of all of these open intervals, a general interval will look like this, n minus half to n plus half. Then the union of all these open intervals will contain the points 1, 2, 3, etc. Right? They're actually this n minus half to n plus half is the half neighborhood of the integer n, right? So it is centered at n, and all the points in this open interval are at a distance less than half from n. So therefore, the set of positive integers is going to be a subset of union n is equal to 1 to infinity, n minus half to n plus half, right? So therefore, this also forms an open cover. There is no overlap here, notice. So let us look at, I think this is clear now, that you have all the uh, positive integers 1, 2, 3, 4, etc. And that is a subset of, so maybe I will try to write it down for you if you like, even though my handwriting is not very good. So I have n, and in the second example, n is equal to union n minus half, that is in n, okay? So n minus half to n plus half. This is what I'm trying to say. So it is not equal to, I will correct it. Just wait. So let me try to write it down just first. So this is n minus half to n plus half, where n is varying from 1 to infinity. So I think you can guess what I'm trying to say. You look at half to 3 by 2 open interval, union 3 by 2 to 5 by 2, 5 by 2 to 7 by 2, etc. And obviously this is not equal to, it is a subset of, so let me just erase this. Okay. So n is a proper subset of this union. So since n is a proper subset of this union is forming an open cover of n. Similarly for this one, right? So since n, for the first example, your n is a proper subset of the open interval 0 to infinity, and hence you can say that open interval 0 to infinity is also an open cover. So at least these two examples where I am sticking for some time is telling you that if you have a set, in this case the set of positive integers, then you can have several open covers of that set, and they may look quite different, right? This has only one element here, and this has countably infinitely many elements, but so this is n. Okay, so I think this is all right. It looks slightly ugly. So I hope these two examples are clear. What you had was that capital A should be a subset of the union of all u alpha, such that alpha belongs to lambda. So here your u alpha is actually your, not alpha but un, where un is equal to n minus half to n plus half, and n belongs to n. So your lambda is actually equal to n in this case. Right? I hope I have made myself clear. So let us look at some more examples that will help us understand these things better. So our next example is an open cover of the open interval 0, 1. So I'm going to construct this. Let us go slow about it. So I have this open interval 0, 1, which is this blue line here, and the gray part is the one which is not a part of this set which we are considering, open interval 0, 1. And I am saying that you look at this family 1 by n to 2 by n, where n is a positive integer greater than or equal to 2, right? So at least it is a family of open sets because it is consisting of open intervals. And what does this look like? Let us just stare at it for some time. If you put n equal to 2, then it becomes half to 1, this open interval, right? And then when you put n equal to 3, you get 1/3 to 2/3. And when you put n equal to 4, you get 1/4 to half again, right? 1 by 4 to 2 by 4. 2 by 4 is the same as half. So you get 1/4 to half. And then you will get a 1/5 to 2/5 somewhere, right? So there is going to be some overlapping. You can see that 1/3 to 2/3 is intersecting half to 1, right? And 1/4 to half is again intersecting 1/3 to 2/3, and so on. So there is some overlapping and all that. And we are trying to say in this particular example that this is going to form an open cover. So what do I have to show? I have to show that if I look at open interval 0, 1, then that should be a subset of union n equal to 1 to infinity, open interval 1 by n to 2 by n. That is my ambition. So for this, you notice that if you take x somewhere here, right? If x is greater than half, then it is in that first set itself, right? You have taken 1 by n to 2 by n open interval where n is greater than equal to 2. So when n is equal to 2, that is the half to 1 open interval. So if x is greater than half, obviously you're taking points from the open interval 0, 1, right? So if x is greater than half, then obviously it is in the open interval half to 1. So it is in the first one itself. So our interest is when x is less than half, then what happens and how to handle it. So we will be using Archimedean property of real numbers. So how are we going to use that? Suppose I take any real number x which is greater than 0 and less than or equal to half. So in this part, right? In the semi-open interval 0 to half, half closed. Now your x is a positive number, so you will be able to get a positive integer p so that px is greater than half. And clearly p has to be greater than 2 because if p is 2, then twice x is actually less than or equal to 1, right? So if you want to get a number which is greater than 1, then you have to multiply x with more than 2. That is clear, right? 2x is less than or equal to 1. So when you are applying Archimedean property, that is ensuring you that you will be able to get a positive integer p so that px is greater than 1, and it is clear that that p has to be greater than 2 because till 2x the number is going to be less than or equal to 1. So it has to be at least 3x or 4x or any number p which is greater than 2. Very good. So we will be able to get such a positive integer greater than 2 so that 1 is less than px. And what does that mean? That means that 1 by p is less than x. So you understand what we are trying to do is that for any x positive which is less than or equal to half, we are trying to find a interval of this type 1 by n to 2 by n open interval so that x will be an element of that. Say for example, even before proceeding with the proof, suppose I had taken half itself. Half is not here, right? But half is where? Half is in 1/3 to 2/3. So half has been covered by 1/3 to 2/3. Now 1/3 is not covered, right? 1/3 is not in half to 1 and 1/3 is also not in the open interval 1/3 to 2/3. So for that you need to look at beyond 1/3, that is if you look at 1/4 to half, this open interval, then 1/3 will be in that. So you get the idea. So that for 1/4 you will have to look at 1/5 to 2/5. That will contain the element 1/4. I think so, right? Yes, let us compute what is 1/5. 1/5 means 4 by 20 and 2/5 is 8 by 20, right? and 1/4 is 5 by 20. So 5 by 20 is clearly between 1 by 5 and 2 by 5. So that is true here. But in general, you will have to just check whether it is true or not. The first part will be okay. That your 1 by, if you take any, say for example, in particular, if you take any 1 by m, then that is going to be greater than 1 by m plus 1. But you also want to ensure that it should be less than 2 by m. Both the things you want, right? So that is what we are trying to do. And instead of looking at the particular examples of numbers of the form 1 by m, we are taking any x, right? So this was our first step. Now let us see what we will do. So you just construct a new set depending on the set x. So that is why I'm calling it nx. Nx is what? Nx is equal to all 1 by n, where n is a positive integer, so that x is less than or equal to 1 by n. So from where am I getting this idea? I know that x is less than or equal to half. So therefore, there is at least one number of the type 1 by m which is greater than or equal to x. So therefore, I am looking at all numbers of the type 1 by n which are greater than or equal to x. So this set, it is at least non-empty because half belongs to this. And what does not belong to this? 1 by p does not belong to this. Because for 1 by p, you know that 1 by p is less than x. So 1 by p is not in nx, right? For any 1 by n to belong here, x should be less than or equal to 1 by n. But 1 by p is less than x. So therefore 1 by p does not belong here. But now notice that if 1 by p does not belong here, then 1 by p plus 1 will also not belong, 1 by p plus 2 will also not belong, because all those numbers will keep on decreasing. So all 1 by m, where m is greater than or equal to p, they will all be less than x. So therefore, what are the numbers which can be greater than or equal to x? Half is there, we know. 1 by p is not there, we know. So the numbers which will belong to this set will be a subset of this half to 1 by p minus 1. It cannot be anything of the form 1 by m, where m is greater than or equal to p. So m can be at most p minus 1. We are not saying it is equal to. We are saying that the number, it may be that half is the only one, right? It could be that nx is just a single term. But whatever, it is going to be a subset of this finite set. See, it is again a finite set. It just consists of how many elements? You start with 2 and you go till p minus 1. So you have p minus 2 elements, right? If you had started with 1, then there would have been p minus 1 elements. So you are leaving out 1. 1 is not there. You're not leaving it out. It is actually not there. So there are p minus 2 elements and nx is a subset of that. So therefore, nx is a finite set. So since it is a finite set, it will have a least element. So let us call that least element 1 by m. So what is our situation? Our situation is that 1 by m is the least element of nx, means it is going to satisfy the defining property of nx, which is that x should be less than or equal to 1 by m. So that is happening. And since 1 by m is the least such, so that x is less than or equal to 1 by m. Therefore, if you look at the next integer m plus 1, for that 1 by m plus 1 will become less than x. It will not be in nx, right? So we will get this situation. So let us look at this diagram. So I have not tried to draw the other points here. We are just focusing on the ones which are interesting to us for the time being. We have this open interval 0 to 1 and we have this half point located here, and x is such that x is less than or equal to half. So for clarity's sake, we have just drawn it to be strictly less than half. It was not necessary. And then what are you saying? You are saying that you have been able to find a 1 by p so that 1 by p is less than x. That was our starting point, right? We had been able to find a p by Archimedean property so that 1 by p is less than x. And then using that and some set theoretic arguments here, what we did was we found a m so that 1 by m is going to be greater than equal to x. Again, for clarity, I have drawn it strictly greater than x. It is not necessary. It may coincide with x. And what is important is 1 by m plus 1 is going to be strictly less than x by the choice of 1 by m, because 1 by m is the least element. So we have this situation. So the only thing which is left out is that I want to claim that 2 by m plus 1 is going to be greater than, strictly greater than 1 by m. So if I can show that, then 2 by m plus 1 is going to be strictly greater than x, and therefore x will lie in this open interval 1 by m plus 1 to 2 by m plus 1. That is our ambition. So let us see. First of all, m is greater than 1 because uh, m is the 1 by m is the least element of half to etc. 1 by p minus 1, right? Where p is again greater than 2. So p minus 1 is greater than 1. So this set has the least element 1 by m. So m has to be greater than equal to 2. This we will keep in mind. So since m has to be greater than equal to 2, at least m is greater than 1, right? So therefore, if you add m on both sides of this inequality, what do you get? You get m plus 1 is less than 2m. m plus 1 is less than m plus m, right? So therefore, you just divide by m plus 1 on both sides. In fact, divide by m into m plus 1 on both sides. Then what will you get? You will get 1 by m here, and you will get 2 by m plus 1 here, right? If you are dividing by m into m plus 1, you just get 1 by m here less than 2 by m plus 1. And this is true because this is true. So what have you proved? Which the thing which was desirable, that 1 by m is strictly less than 2 by m plus 1. So therefore, what have you got? You have got that 1 by m plus 1 is strictly less than x is less than, strictly less than 2 by m plus 1. So x belongs to the open interval 1 by m plus 1 to 2 by m plus 1. So you have been able to find an interval of the form 1 by n to 2 by n open interval where x will belong. And x was what? X was an arbitrary point less than or equal to half and greater than 0. For x greater than half, you have already got an open interval where x will belong. And for x positive less than or equal to half, after a little bit of work, you found an open interval of this type where x will belong. So what have you done? You have taken any random element of the open interval 0 to 1, and you have shown that it will belong to one of these open intervals. So it is a subset, open interval 0, 1 is a subset of the union n equal to 2 to infinity 1 by n to 2 by n. And hence, this family which we had written in the very beginning, script u equal to 1 by n to 2 by n, where n is a positive integer greater than equal to 2, this is forming an open cover of open interval 0, 1, right? So you had to do some work to prove this. And if very trivial question could be that why did we start with n greater than equal to 2? Because if n was 1, then it would have been the open interval 1 to 2, and that is redundant. Why take the open interval 1 to 2? We want to cover the open interval 0 to 1. So why take something which is disjoint from open interval 0 to 1? So that is why we have left it out. Okay. So I hope I have been able to explain this. Let us look at another example of the same set. That is, we are looking at the open interval 0, 1, but now we are looking at a different family. Again, I am naming the family script u. That is not important, but it is a different family. What is it saying? You look at the family of all open intervals of the type 1 by n to 1 minus 1 by n. And here I am taking all positive integers which are greater than equal to 3. So let us first determine y greater than equal to 3. Okay. So if I take n equal to 1, then what is happening is that this is an empty set. because if n is equal to 1, then this is open interval 1 to 1, right? No, no, sorry. This is open interval 1 to 0. So therefore, that is a empty set. There is no real number which is greater than 1 and less than 0. Therefore, the n equal to 1 doesn't make sense. Therefore, we don't take it. And what about n equal to 2? That is also empty set, because 1 by n is half in that case. So you are looking at open interval half to half, right? When n is equal to 2. So that means all real numbers which are greater than half and less than half, which is not possible. So therefore, the first two intervals of this type for the first two values, n equal to 1 and n is equal to 2, they're actually empty sets. So it doesn't make sense to include them in a family which I want to be such that the union of all its members should contain open interval 0, 1 as a subset. So therefore, we are leaving it out. Okay. So what happens when n is equal to 3 onwards? So let us look at a few examples. It's not very difficult now. We have learned lots of things about sequences. So you can see that 1 by n is going towards 0 and 1 minus 1 by n is going towards 1. So these open intervals are actually gradually expanding. If you put n equal to 3 here, you get open interval 1/3 to 2/3. If you put n equal to 4, then you get 1/4 to 3/4, right? 1/4 to 3/4, then you will get 1/5 to 4/5. 1 minus 1/5 is 4/5, right? And so on. So it will keep on expanding. And we want to say that this is an open cover of 0, 1. So the first example, what was maybe not so obvious, but this intuitively is uh, at least believable that it is expanding towards these 2 points, 0 and 1, and therefore it will cover it. But to prove it, we will again uh, go systematically. So how? We will take any when any point in the open interval 0, 1. So then we will look at the numbers x and 1 minus x. So x is also positive and 1 minus x is also positive, right? Because x is less than 1, so 1 minus x is greater than 0 and x is greater than 0, clear, given. Okay, so both are given actually. Since x is a point in the open interval 0, 1, both x and 1 minus x are positive numbers, and therefore by the Archimedean property, you will be able to get two positive integers, p and q, which may be different. That is the issue. So that one is less than px and one is less than q times 1 minus x. So what do you get if you arrange this properly? You get that x is greater than 1 by p and is less than 1 minus 1 by q. So you see, you're almost there, but not quite. Because if P were equal to Q, then you would have got the type of interval you were seeking. Again, you're trying to do the same type of thing. You're taking any point in open interval 0, 1, and you're trying to find an open interval of this type, 1 by n to 1 minus 1 by n, so that x belongs to such an open interval. So Archimedean property is at least ensuring that you will get an open interval of the type 1 by p to 1 minus 1 by q, where x will belong. But the p and q, the numbers which you get, may be different. So a little bit of rearranging your numbers will just give you the proper interval. What do you have to do? You just take the maximum of P, Q and 3. Why does this 3 come into picture? Because in our family, we had to take, we were forced almost, because we don't like to think of empty sets here. So we were almost forced to take positive integers greater than equal to 3. So we include that 3 also there. So we take the maximum of P, Q and 3. So suppose that is n. So what is happening to 1 by n? Since n is greater than equal to p, so 1 by n is less than or equal to 1 by p, and 1 by p is less than x, right? So what happens to 1 by n? 1 by n becomes strictly less than x, right? I've tried to draw the figure with the necessary points only. I have left out the other points. So I have this x point in the open interval 0 to 1. So by Archimedean property, I have got this 1 by p, and I have also got 1 minus q, so that x lies strictly between 1 by p and 1 minus 1 by q. And now I have just done this small trick that I have taken n to be the maximum of p, q, and 3. That is going to solve your problem. 1 by n is less than or equal to 1 by p, but 1 by p is strictly less than x. So 1 by n will be strictly less than x. Again, x is strictly less than 1 minus 1 by q. And what can you say about 1 by n again? 1 by n is less than or equal to 1 by q. So minus 1 by q is less than or equal to minus 1 by n. So 1 minus 1 by q is less than or equal to 1 minus 1 by n. I have drawn it to be strictly greater, but they may be equal. That is not the difficulty. Because you already have that x is strictly less than 1 minus 1 by q. So x is going to be strictly less than 1 minus 1 by n. Therefore, x is going to belong to this open interval 1 by n to 1 minus 1 by n. Right? So it was very simple. And what did you get? You got that if you take any arbitrary point in the open interval 0, 1, you will be able to get an open interval of in the family script u, right? So that x will belong to that member. So therefore, if you're taking the union of all the members of the family script u, open interval 0, 1 is going to be a subset of that, right? So therefore, this family script u, 1 by n to 1 minus 1 by n, that also covers open interval 0, 1. Generally, people like to explain covers by talking about a tablecloth covering a table. So if you like, you can think of it like that, but you can see that it is not quite happening when we look at these examples. Because when we are talking about tablecloths covering tables, we are always assuming that there is something extra which is left out, right? More than the set. This happened in your first example. Where is it? This example, that you had the set of positive integers, and the cover which you took here as well as here, it had some many more extra points than the set itself. So you can, the exact imagery of covering a table by a tablecloth with some part of the cloth hanging outside the table is okay here. But for this particular example, right? For this particular example, notice that all the subsets which you are taking, they are all the members of this family, which is covering 0 to 1. They are all subsets of the open interval 0, 1. So you are covering it, but just covering it, right? You are not going beyond the set. Similarly, for the this particular example, here also the same thing is happening. You are covering the set and covering it by subsets of the given set, right? So as if from the inside you are covering it to covering this particular open interval. So that imagery is not quite correct here. You can almost say that I had not much of a cloth, it just was of the same size as the table or something. But okay, I hope I have made myself clear that it is not necessary that there will be something superfluous. It may be exactly inside this. Okay, even though I have not bothered to write that here, but that type of thing may happen. Okay, so these were interesting examples, which we will see why later on again, because we'll come back to them. But now suppose I take my subset as the whole of the real line. Then can I construct an open cover of that? There actually I have no problem. If I look at the family of all open intervals of R, look at any open interval of the form AB, where AB are real numbers and A is less than B, then obviously your R is going to be a subset of all the union of these open intervals AB. Because if you take any number x, real number x, you can always look at the open interval x minus 1 to x plus 1. And that interval is in this family. Therefore, x will belong to open interval x minus 1 to x plus 1. And hence, this script u is going to form a cover of R. Now you notice that this cover is quite different from the ones which we saw till now. The first one was a very trivial thing, it was just a singleton. Then we looked at some examples of covers where the covers family was a countably infinite family. And this one is an uncountable family. Because how many open intervals are there? At least as many as real numbers are there. For every a, you are getting at least one open interval of the form a to a plus 1, right? So since r is uncountable, this family is also uncountable. But this example is telling you something a little bit more, that if you don't look at this whole family and you choose certain number of members of this family. So what am I saying is that choose uh, intervals of the form n to n plus 2, where n is an integer. Then I want to say that this will also cover your real line. And why can we say that? Because if you take any real number, x, then you know that box x is less than or equal to x, right? And x is less than box x plus 1, because box x means what? It is the greatest integer less than or equal to x. So you do have such a situation. So just look at box x minus 1. So box x minus 1 is strictly less than box x. So box x minus 1 will be strictly less than x, and that will be strictly less than box x plus 1. And box x is what? Box x is an integer. So therefore, for any x, you are able to get an interval of the form box x minus 1 to box x plus 1, right? So box x minus 1 plus 2 is exactly box x plus 1. So it is an interval of this type, and it contains the open interval x. So if you look at only these open intervals, then that is also covering the real line, and from where you have extracted this new family, you have extracted this new family from this original one, which consisted of all open intervals of R. From there, you are looking at some specific open intervals, and you are saying that they are also able to cover R. This leads us to a notion which is called a subcover. So what does that say? That says that if you have any family script U alpha, alpha and lambda, which is an open cover of a subset capital A, and if you look at a subfamily U alpha, where alpha is in some lambda prime now, where the index at lambda prime is a subset of lambda. Okay, so that is what was happening here. Here, lambda was R. Actually, it is equal to R, but why is it equal to R is beyond our course. So I'm not going there, but at least it is something which is more than a countably infinite set, right? Because it is an uncountable set. And Z is clearly going to be a subset of that. So from that lambda family, if you believe lambda equal to R, it is easier to understand. Then Z is clearly a subset of R. So that type of situation is happening. That suppose you can construct a subfamily from this new one, so that if you take the union of U alphas where alpha now belong to lambda prime, that is also an open cover of A, then you will call U prime a subcover. But now the languages, this is something which generally confuses people who look at it for the first time. The language is that U prime is a subcover of U, right? Because here what we are doing is that we are fixing up this A. This is very, very important, because unless you fix this A, you cannot talk of things like this members of the family U prime will also cover A, right? A has to be a subset of union U alpha, alpha and lambda prime. So your A, once your A is fixed, then if you look at an open cover, and if you get a subfamily of that open cover, which also covers the same set, then you will call it a subcover. So now your set is fixed, your cover U is changing, right? Script U is changing. So therefore, This subfamily is not called a subcover of capital A. Mind it. A is fixed. Script U prime is called a subcover of the given family U. So that we will remember. Okay. Now what is the next result, which is a very, very interesting and important result, but we will not prove it. It is called the Lindelof covering theorem, which tells you that any open cover of a subset A of R will always have a countable subcover. That is what we saw in this example, right? Out of an uncountable family which was covering the real line, we could obtain a countably infinite family which still covered R, right? So this is what Lindelof's theorem is telling you, that this is always possible. Whatever subset A of R you take, if you take an open cover of that set, it will have a subcover which will contain countably many elements. So countably many elements means either finite elements or countably infinitely many elements. Okay. The proof depends on the fact that rational numbers are dense in R. Right? We have seen that between any two real numbers, there are infinitely many rational numbers. And secondly, we know that the rational numbers, the set of rational numbers is countable. So using these two facts, you can actually prove this theorem, but we will not do it because it is not in our course. Our next result, I'm not going to look at any result in this particular lecture. Next notion is that of a compact set. So what we know by Lindelof's theorem is that any open cover will of any set, fix a set capital A, take any open cover U of that set capital A, you will always be able to extract a countable subfamily which will cover it. So the next interesting part, and actually it becomes very interesting, is the type of sets for which if you are given any open cover, you will be able to extract finitely many members from that open cover which will still cover the set capital K. So such sets are called compact sets. And we also say that a set satisfies Heine-Borel property if every open cover of capital K has a finite subcover. The reason for this is the Heine-Borel theorem, which we will see in a subsequent lecture. But right now, let us just focus on this. So what am I trying to say? That whatever open cover of capital K you get, you will always be able to choose finitely many members of that open cover which will still cover K. This will always happen. If that is true for a set capital K, then the set is called compact. And this is going to be our focus in the next few lectures. So let us look at one or two examples here. The first example is a simple one. Take a non-empty finite set. So capital A itself has only finitely many elements, x1, x2, etc., xm. Okay. And suppose script U is any open cover of A. Then what will you do? So script U looks like what? We have written it down, U alpha, such that alpha belongs to lambda. Now what you do is that for each of these elements, x1, x2, x3, etc. till xm, for each xj, you choose alpha j in lambda so that xj belongs to u alpha j. Why can you do that? Because this is an open cover of A, right? So A is a subset of union of u alpha, alpha and lambda. So therefore, every point of capital A is at least is a member of at least, is an element of at least one of the u alpha, right? So let me repeat it again. Since script U is an open cover of capital A, every element of capital A is an element of at least one u alpha in this family, right? Because capital A is a subset of union of u alpha, alpha and lambda. So therefore, if you fix your xj, there will be at least one where xj will belong. So choose that. I don't want to say choose that, because there may be many, but there will be at least one. So choose one of them and call that alpha j just for our notational convenience. So suppose alpha j is the index, so that xj belongs to u alpha j, and you can guarantee that you will always get such a alpha j, because script u is an open cover. So then what have you done? You have chosen M open sets. U alpha 1 which contains x1, U alpha 2 which contains x2, and so on, U alpha M which contains xm. So this new family, which contains only finitely many, only M many open sets, this is a subfamily of script U, right? And this clearly covers capital A, because x1 belongs to U alpha 1, x2 belongs to U alpha 2, and so on. Xm belongs to U alpha n. Therefore, A is a subset of U alpha 1, union U alpha 2, union etc., union U alpha. So this is also a cover of capital A, and it has only finitely many elements. Hence, capital A is a compact set by our definition. This was any open cover, it has a finite subcover, so A is compact, right? And similarly, if you look at the empty set, then it is clearly compact, right? Because whatever family, suppose you take such a family, then you just choose any one element from the family. Empty set is a subset of every set. So empty set is a subset, just fix a alpha and take U alpha. Then look at the singleton subfamily U alpha. Then empty set is going to be covered by that singleton family also, because empty set is a subset of U alpha. So clearly empty set is also a compact set subset of R. So let us see, maybe I will do this example and only this example. Okay, so this one will be the last example, and we will stop here. We will continue in the next lecture. So this is the first one which we had, right? Open interval n minus half to n plus half. So let us go back to this one and see what it looked like. So this is this one, and this had only one thing, right? So trying to find a sub family which is finite from this one doesn't make any sense. So we just want to see whether this family will have a finite subfamily or not. So what is happening? See, again, look at this picture. If you look at any n minus half to n plus half, that will contain only the positive integer n. It will not contain n minus 1, it will not contain n plus 1. So it will not contain any positive integer less than n minus 1, it will not contain any positive integer greater than equal to n plus 1. So this open interval has only its intersection with the set of positive integers is just singleton n, right? If you look at any open interval n minus half to n plus half, then its intersection with the set of positive integers is just n. So if I drop even a single one, suppose I drop half to 3 by 2, then 1 is left out. You can no longer cover 1. Similarly, if you leave out 3 by 2 to 5 by 2, you can no longer cover 2, and so on. So if you leave out any of this n minus half to n plus half, even one of them, then it will not cover the number 1, number n, sorry. So therefore, you cannot extract. Finite is a different question altogether. You cannot leave out even a single one. You need all of them to cover the set of positive integers. Therefore, this cannot have a finite subcover. So that is our last example in today's lecture. That if you look at this family, n minus half to n plus half, then since this, if you choose any one of them, its intersection with the set of positive integers is just singleton n. So therefore, this family will not have any finite subcover. Now, what was our definition of compact set? The definition was that every open cover, let us go back there, okay? Every open cover of capital K should have a finite subcover. So if you can find even one open cover of capital K which does not have a finite subcover, then K will not be compact. For it to be compact, every open cover should have a finite subcover. I'm just repeating myself. And therefore, in this case, the set of positive integers, you have been able to find one open cover which has no finite subcover. Therefore, you can immediately say that the set of positive integers is not compact. So I suppose I should stop here, and I will insist that you should please go through this. Otherwise, you will not be able to understand the subsequent lectures. Let us just stop here.